Sir, we'll wait for 4 minutes, another 4 minutes, let others join, sir.
Which session start? Okay, good evening all. We are honored to introduce Professor P. Naveen Kumar, Department of ECE, University College of Engineering, Usmania University, Hyderabad, Telangana. Professor P. Naveen Kumar sir has obtained his PhD in Electronics and Communication Engineering from Usmania University. He has published around 120 research publications in various reputed international and national journals, conferences. He has also successfully completed several major and minor research projects from Space Application Center, ISRO, Department of Science and Technology, Government of India, World Bank and etc. He has established in Usmania University a state-of-the-art and advanced GNSS research laboratory in collaboration with ISRO, which was inaugurated by the chairman ISRO, Sri A.S. Kiran Kumar sir, during the centenary celebrations of Usmania University in the year 2017. He is instrumental to establish a new Usmania TV, which is the first university in the country to have its own satellite TV broadcasting channel for transmitting its educational content in association with the Department of ITENC, Government of Telangana. He is the nodal officer for several MOUs with Usmania University, such as NRSC, ISRO, CMET, OTH University, Germany, SAC ISRO, TSAT, Government of Telangana, etc. He has over 25 years of teaching, research, and administrative experience, successfully guided around 15 PhD scholars who were awarded with PhD degrees in the recent 84th convocation of OU. He has visited several countries, including USA, Japan, Germany, Malaysia, Italy, Vatican City, Oman, Thailand, etc., on various academic and research assignments. He has received several prestigious national and state awards. Professor Srinivasan IETE Memorial National Award 2024, CHSN 2020 Young Researcher Award, Award for Excellence in Research, Usmania University Vice Chancellor Award 2022 for Research Excellence, so C.V. Raman Memorial Award 2019, and Dr. Vikram Sarabhai Memorial Award 2024, and Best Research Paper Award. He is instrumental in design and development of OU website in 29 multilingual languages, introduced QR code based infra as asset tracking system in OU, special mobile application for women or girls of OU. He is a member of many central and state government committees and several governing councils of leading academic institutions. He has introduced global navigation satellite systems with Indian constellation called Indian GPS course and laboratory in the UG and PG curriculum and laboratory course in PG course at Usmania University. Professor P. Naveen Kumar served as Vice Chairman, IETE Hyderabad section. He is fellow member of various professional societies, FIETE, FIE, and a member of other professional bodies such as MBES, MIACST, Singapore, MISOI, MOGI, etc. He has delivered many invited talks at various R&D institutes, NRSC, academia, etc. He served as a chairperson board of studies, university level, and currently is professor and head of the Department of Electronics and Communication Engineering, University College of Engineering, Usmania University. Thank you, sir. On behalf of brilliant group of institutions, welcome, sir. And now I hand over the session to Professor P. Naveen Kumar, sir, to continue the session. Thank you, sir.
Yeah, thank you so much for your introduction. I hope you are able to hear my voice.
Yes, sir. It is clear, sir.
Yeah, thank you. So I'm very happy to be part of this particular program. So my topic is on GNSS signal structure and the characteristics. So I'll just give the brief of overview of all the different aspects and talk a little bit more about the modernization program also and the different things. So the outline of my presentation goes this way. I'll talk about the introduction, then GNSS, GPS, errors, IRNSS, what is the current status, then satellite-based augmentation systems. In that, I'll also be talking about ground-based augmentation systems and applications and then conclusions. So we all know this. Can anybody tell what is this particular tall structure? Anyone who knows this? Is there any resound actually you're getting?
Sir, it is clear, sir.
This clear? Okay, thank you. So this we might find in most of the airports. It's an air traffic control. Okay, so here what we do is on the top of it, it's an air traffic. On the top of it, you find the air traffic controllers sitting there and communicating with the pilot, and also they guide them where to land and take off. There a proper communication link is to be established. So this plays a major role. So in fact, we define the term that is CNS, communication, navigation, and surveillance. So if we imagine in civil aviation, that is the airport, the navigation will tell the pilot where he is, and the surveillance will tell the air traffic controller where the pilot is, and communication between these two will play a major role. So it's very extremely important that there should be a proper sufficient communication should be there in this particular system. So, but currently, because some of the things are implemented by ground-based systems, they have a lot of issues with the propagation limitations or compatibility between different CNS systems in different parts of the world and lack of digital air-ground change. So what there is, International Civil Aviation Organization. So they established a new committee, which is known as FANS, Future Air Navigation Systems. And their purpose is to look after SACNS, Satellite Aided Communication, Navigation, and Surveillance. So once you have this, communication between ATC and the pilot, satellite aided, instead of ground-based systems, then it will facilitate the universal accessibility and ability to protect safety communications from harmful interferences. So this will, because the aircrafts will have a different equipment, they may be manufactured by different countries, and the airport may be a different thing. So those issues will be there. So now the target is to have all these airports with SACNS. So ultimately, GNSS will talk about the position. In fact, we want to know what is the user position. So we all know that, 0 degrees latitude, if you go towards up, you get 30 degrees, 60, 90 degrees towards the north. Horizontal lines are latitudes. Vertical lines are, longitudes. So if you move this side, it will be 90 degrees east. And if you move this side, it will be 90 degrees towards the west. So if you look at the Hyderabad position, you may have around 17 degrees towards the north and 78 degrees towards the east approximately. And no 2 points will have same latitude and longitude. In fact, our whole process will depend upon the actual user position and how accurate it is there. So history has changed when first artificial satellite Sputnik was launched. In fact, there was a lot of technological war was there between the Russia and US, but somehow Russia has taken up the first artificial satellite in space. So since then, satellite-based communication and navigation, the fields have taken a lot of advancements, and finding the orbit of the satellite led to the concept of satellite-based navigation. Just let me see, because I got a message that there's echo is going on. Hello, is it okay now?
Okay, sir.
Yeah, that's nice. Okay. I'll just check. So now what is happening is first artificial. Thank you. Yeah. So since then, a lot of work has been done, and finding the orbit of the satellite led to the concept of satellite-based navigation. Then there was a project, United States, they have taken up in the year 1963. So based on that project, US Air Force, they initiated a project 621B, which eventually evolved into NavStar program. NavStar stands for Navigation, Satellite Timing and Ranging Program. And one of the objectives of this program is to guide a Trident missile it's a submarine launched ballistic missile equipped with multiple independent target re-entry vessels. So that Trident missile should be, guided, and it has to hit the target. So since then, that particular why it has been taken up. So this is the the missile, which is a Trident missile. So where they are being launched through this particular project. We'll talk about GNSS. In fact, GNSS stands for Global Navigation Satellite Systems, and it refers to the worldwide positioning, navigation, and time determination capability available from one or more satellite constellations. So we all know that most of the people know only GPS, which is a global positioning system developed by US, but there are other GPS systems which are already available. Russian GLONASS is there, European Galileo, and Chinese BDOG is also there. So these are all different global systems, and other regional systems are NAVIC Indian constellation, then Japanese QZSS, and BDO-1 Chinese system. The ultimately for all these systems, they have to provide the position, they have to provide the accurate time, and they have to provide the navigation. And some system provide the global, and some are, regional systems. Collectively, we can call them as GNSS, Global Navigation Satellite Systems. So across the world, GPS, because it was very successfully evolved, and most of the people know GPS, but there are many other things. Even during the Russian Ukraine war, the Russia has used its GLONASS as their own system for military applications. So in fact, before GPS, there was one more system which was there, that is known as Transit. Transit was the world first satellite navigation system. But in fact, that was discontinued because it was not able to provide accurate position. It was having around 100-meter accuracy. It is to give the initial fix about half an hour, and weather also was going to affect and all that. So it was used for US Navy and all that for some time. But later a lot of issues went on, and in 1973 US Department of Defense, they decided to establish, develop, test, acquire, and deploy this GPS. And then since then, they started a lot of work and launched many of the satellites. And finally, 24 satellites were launched 1995, and they declared it operational. And then they transmitted the satellite signals, GPS satellite signals across the world. And wherever you have the compatible receivers, they were able to receive the signals. And in fact, GPS was originally named as Navstar GPS. It is navigation, satellite timing, and ranging. It's an all-weather space-based systems, and GPS satellites have got a lot of radio transmitters, atomic clocks, which is responsible for providing the accurate time, and also various equipment for positioning and all other things. So here we have a figure which shows the blue one is the receiver, and here we have these are the orbits, medium Earth orbit at a height of 20,200 kilometers, and then we have the red dots and blue dots. So this receiver, whenever it is, it depends on the latitude and longitude, and at particular point of time, it may receive signals from 12 satellites or 5 satellites, 7 satellites based on the time, day of the time, and then seasons, and even the position, etc. So even though there are 24 satellites are there, the number of satellites visible to the receiver, or the receiver receiving the signals, will keep on changing from point to point. But at any point of time, at least a minimum 4 satellites are required to know the user position, and without that, they'll not be able to get the information and not be able to provide the user position. Now, this is the architecture of GPS, like that of the architecture of GPS is similar to that of all other constellations. It has got space segment, it has got control segment, and user segment. Space segment consists of all the satellites, GPS satellite constellation, and control segment has got the monitor stations, master control stations, and ground antennas. And monitor stations are being kept at different locations across the world, and a master station. The monitor station will be able to collect the information from all the GPS satellites, and they send it to the master station. A master station will be able to calculate, it is able to calculate the corrections, and then from there those corrections are being sent to the ground uplink station, In the ground uplink station, you have the ground antennas, and from there information is sent to the satellites. So these satellites will apply those corrections and then retransmit back to the user. The user will receive the signals and the corrections, and then therefore they get a proper user position. So GPS has got totally 6 orbits. All the 24 satellites have been placed in different orbits. And later US has launched many more, few more satellites, and currently 32 satellites are there, and then one is decommissioned, 31 are in operational now. And here we find A, D, and all that. These are the names of the orbits, and C3 means C orbit with 3 satellites, third satellite, and they're continuously moving in their orbit, providing the signals in L-band 1 to 2 gigahertz to all the receivers across the globe. So you can have unlimited number of billions of receivers on the ground, and you'll be able to receive these particular signals, and they can be used to calculate the position, navigation, and timing. All the P&T applications can be made easily. Now, all these satellites are not launched in one go, but they are launched in different blocks. So 15 satellites were block 2A, they were launched and they're in operation. 12 block 2R and 4 block 2R satellite, they're all been in operation till now. Now here, this is a little bit more information, and here in the control segment, if you look at here, these are the locations where the monitor stations are being kept, and master control station where it is kept, and upload stations, and the process is similar whatever I explained here. So all the satellites signals will transmit information in L-band, and then the corrections is ephemeris corrections, clock corrections, ionosphere data collections, and all that will be sent to the satellites. Satellites will send those corrections with the signal to the GPS receiver, and this is a continuous process, and therefore you get the proper positioning applications. GPS would be able to transmit the signals in L-band. So there are many signals are there, L1, L2, L3, L4, and L5. L1 is for about 1.5 gigahertz, L2 is 1.2 gigahertz, L3 is 1.3, and L4 is again reserved for military applications. And in fact, we all have access only to L1 CBA code, L1 signal only for all our civilian users. We'll talk about L5 at a later stage when we talk about a modernization program. So L1 signal, in that you have CBA code and P code, and across the world, all the civilian users will have access to L1 CBA code only. And then L2 is it is a 1.2 gigahertz. It has got P code, and it is used only for Department of Defense for military applications of US. And then L3 1.3 gigahertz is for nuclear detonation detection, and L4 is also reserved for military applications of US. So across the world, we have access only to L1 CBA code only. And why do we require 4 satellites? In fact, signals, if the if the receiver was able to receive signal from one satellite, then the user can be anywhere in this particular sphere. And if the receiver GPS receiver receives 2 satellite signals, then the user position can be anywhere in this particular intersection of these 2 spheres. It's not sufficient for us to know their position. So therefore, third satellite signal is required. Then you get 2 different points where the ambiguity is there. But to resolve this ambiguity, you require a 4th satellite, and 4th satellite signal will be able to provide the time bias, and it will be able to resolve this particular one, and you'll be able to get a pinpoint position. So therefore, you require at least 4 satellites minimum are required to know the user position to get accurately. Without that, will not be able to get a proper position. You may get a position, but it will be an error. And GPS will be able to provide 2 different services, that is SPS and PPS. So SPS stands for Standard Positioning Service, and PPS for Precise Positioning Service. Standard Positioning Service is a service which is provided to all the civilian users. It's a free of cost, and anyone having a compatible receiver, they'll be able to receive these signals. And PPS is a Precise Positioning Service. This service is only accessible by US Department of Defense for precise positioning applications. They get a very centimeter pinpoint positioning and use for all those defense applications of US. Now we get an error, GPS, we will not be able to get a pinpoint positioning for civilian users. It's all because of different types of errors, because GPS signals need to be transmitted from at a height of 20,200 kilometers. So they have to pass through the ionosphere, troposphere, and all that. And by the time they reach here, a lot of issues will happen to the signals. Now you can observe this particular diagram. So here, what we have is, the satellite signals have been transmitted and it has to go through ionosphere, it has to go to troposphere. And in the ionosphere, a lot of ions and electrons are there where the signal will have an issues. It has to interact randomly, and then a lot of issues will happen, and that will introduce an ionospheric error. And troposphere, it has got water vapor content, and that is introduced a troposphere error. And then later, you will have multipath signal. Instead of getting a direct signal, you get a reflected signal, and that will introduce a multipath error. And even on the the receiver also, you have an inherent noise which is generated and all that, and that will introduce a receiver noise. So many things will happen by the time the signal is being received to the by the receiver. So, and it will introduce so much of error. So if you look at the SPS budget, satellite clock will introduce around 1.5 to 3.6 meters. Orbital error will introduce around less than 1 meter. Ionospheric phase is the most predominant error, introduced around 5 to 7 meters, especially for SPS services. Then receiver noise will introduce 0.3 to 1.5 meters, and multipath is around 1.6 to 1.2 meters. So it's so much of these errors need to be modeled so that you get a pinpoint position. So that's very important. Clock error. It is, it's caused by slight discrepancies in the, each of the satellite errors. Then orbital errors, satellite orbits set into altitude, position, and speed of satellite. Their orbits will vary due to the F1, F2 forces acting on the satellite, the centripetal and centrifugal forces which are going to act on the satellites continuously. And when there is any balance is missed out, then satellite will be moving out of the orbit, and that will introduce some issues. And similarly, ionosphere interference is there for the signals. So GPS satellite signals, they'll be refracted as they pass through the Earth's atmosphere, and causing the signals either to slow down or speed up and all that. Similarly, troposphere also has got an issues. So that will that's another part which will be it is there, and that is due to large of the water vapor content. And as I said, receiver noise, it will have internal electronic generated, which will because of the EM fields, they tends to distort the radio waves. And later, multipath also, instead of getting a direct signal, you get an indirect signal, and that will introduce. Each one is a very, very big error, and they all need to be modeled so that you get a pinpoint position. And earlier I said that, apart from the 4 satellites, in which direction you need to receive these particular signals. So, you can get a big spread here, but here if you look at that, all the 4 satellite signals are received only in one direction. So then we call it as a poor DOP, GDOP. DOP stands for dilution of precision. It indicates the quality of satellite geometry. And if you get in different direction at return space, then you can call it as a good GDOP. So, the ideal value of DOP is around 1. And practically may get around 1.5. So the better the DOP value is, the better the user position will be there. So DOPs can be divided into different terms, that is geometric DOP, position DOP, horizontal DOP, vertical DOP, and time DOP, and all that. So satellite geometry definitely is going to affect the quality of the GPS signal and accuracy of the receiver trilateration. So DOP will reflect each satellite position related to each other's being accessed by the receiver. So it's important that 4 satellite signals having very good signal strength to be received by the receiver, and also it should also have a good DOP value. These are very, very important aspects of these particular things. So this is an ideal geometry which we say. There are good directions are there, and this is another one. So you can see ideal DOP value is 1 here. That's the another one, and but if you receive the signals, even if it is too wide, then also it's not appropriate. Here you are receiving signals in one quadrant, so you'll get a very high DOP and you'll not get a proper positioning. So like this. So here you may have a very tall structure, and it may the other satellite signals may not be received. GPS signals cannot pass through the concrete structures and or steel buildings. So therefore, this side you may not get, and only one side you get it. Then you'll have an issue with the position accuracy. So these are all the issues with the existing GPS signals. In fact, all the GPS signals currently, this existing GPS, we call it as a GPS 2. And it has got L1, L2, L3, and L4. And the current GPS signals, they will not be able to have a proper indoor positioning applications are not there. And there are some parameters which are known as required navigation performance parameters. They are accuracy, continuity, availability, and integrity. These parameters are also been not sufficient for existing GPS 2. So US, what they did is they would like to go for the next next generation program. So it is known as GPS modernization program, and it is also known as GPS 3. So now we will see what are the different things which are there in the GPS 3 program, and then so here we look at the plans. What are the different plans it has got? Here we talk about why this GPS modernization program should be taken up. What is the current constellation? What are the objectives of this GPS modernization program, and how far it has come, and what are the new signals? What would be the future application if this is implemented, and all that. So if you look at here, like internet, GPS has become a very critical component of global information infrastructure. And it is very, very important that, GPS, it is there in every application of it. And it has become a global utility providing space-based PNT applications. And if the current issues have been addressed, then by augmentation system, the performance can improve to much bigger one. So what is the necessity of the GPS modernization program? So currently, standalone GPS means it is not integrated with any other system. We have access, civilian users have access only to L1. And L1 has got only C by code and P code, and we have access only to L1 C by code. C by code is for course by acquisition code, and P code is for precision code. So all the users across the world will have access only to L1 C by code and not to the P code. P code is very highly encrypted and can be decrypted only by USD. And unless until we have two different frequencies, we'll not be able to minimize the ionospheric delay so that you can get a very precise positioning. And apart from that, another issue is L1 and L2 signals are not afforded total spectrum protection, and they're relatively weak due to background noise. That's another issue. And existing GPS signals cannot penetrate into concrete structures and steel buildings, and they are, are undergo and are susceptible to interference and jamming issues are there. And reflected signals, that is multipath error, is also going to cause positioning error. So in fact, protection from the hostile GPS is very, very important apart from the user's people. And in case if you don't have access to L1 CBA code, there is no other redundant signal you can use for your GPS application. That's another biggest, another issue which is there. So therefore, even though we have 31 satellites, these are all belong to existing GPS 2. So these are all having all these issues are there. So, what we require in GPS modernization program is we require a system-wide improvement in accuracy, availability, integrity, and reliability. That's accuracy is your user position should be more accurate. Availability, whenever you switch on the receiver, you should be able to receive the signals. Integrity, even in case of critical applications like civil aviation also, where safety of life is very, very important in those few seconds, and all that integrity will play a major role of the signal. Reliability is it should have worked successfully for over a period of time, and backward compatibility should be there. Robustness against interference, improved indoor mobile and urban use, interoperability with other GNSS, not only GPS modernization. If you want to use one with GLONASS, Galileo, and one GPS 3, it should be able to give you still the best position and all that. So therefore, all these objectives are there for GPS modernization program. They all need to be taken up. So in this program, the new signals which have been added is existing. You have a CBA code, but on that again, they would like to add. It is there on L1 frequency, but on L2 you don't have a CBA code. So what they did is they would like to add the other C by code on L2. So it's L2 will have a C by code again. And existing signals GPS2 have P code, but now new GPS3 will have M codes, that is military codes, which they would like to add on L1 and L2 frequency. And then for civil aviation applications, this additional C by code on the L2, it is not sufficient due to potential interference from the radars which operate on L2 band. Therefore, you require another new signal is required, that is L5 signal. L5 signal is for 1.1 gigahertz, and that signal is known as safety of life signal, especially it is for civil aviation applications used, and it lies in the aeronautical radio navigation system band also. And if you want to implement all these new satellites with new signals, definitely you require new Block 3 satellites, and also you require a new control segment. So it is targeted that GPS3 modernized satellite signals and control segment will be launched, and they will become operation by the year 2030. So currently around 4 to 5 satellites are already being launched, and a lot of test work is going on, and the work is in progress. So this project would involve the development of new ground stations, new navigation signals for both, and also aim to improve the accuracy, availability for all the users. There were two major companies which have been given. That is the Lockheed Martin. They were awarded this contract and development of design and development of GPS3 space pregnant. And Raytheon, another one, they were awarded with the next generation GPS operational control segment. They were also there. So Raytheon should look after the ground segment, and Lockheed Martin should look after the space segment. And that's what the target has been given. Now, this is the pictorial view of the GPS3 constellation. So unlike you have a GPS2 here, also you have the altitude will be around 20,181 kilometers, and proposed to launch 27 satellites in 6 orbital planes, and you'll have a similar kind of inclination angle around 55 degrees and all that. And here you will have all GPS3 new satellites which will transmit L1 signal, L1C signal, L2C, L5, and you have M codes. And apart from that, you have a 20 dB spot beams, which is available. In fact, it will give you a lot of power during that awareness, more increased, resolutions and all that accuracy will be available. And especially it will help the US DoD in case of the wars and other things. And whereas the operation, everything will remain the same. So this is a new particular feature which they have, incorporated in GPS3 segment. So GPS3 satellites will transmit a very high signal power at the Earth's surface when compared to GPS2, and they have a very high powerful M codes are there, and L1 and L2 will have minus 157 dBW for CBA code signal and minus 160 for P code, and L5 is for minus 154. And there is another important point which is there for Block 3 satellites is they would carry laser reflectors. So this will help the orbits of satellites independent of radio signals. They'll help in the tracking the orbits, and also they allow satellite clocks to be designed from ephemeris error and all that. In fact, this is also a standard feature in case of Russian GPS and also European GPS systems, and they've also included in their architectures. In fact, existing GPS will have only L1 and L2 signal. And on L1 signal, you have a C by code and P code. And on L2 signal, you have a P code only. There is no C by code. So therefore, in the next Block 3 satellites, they are going to add P codes on both L1 and L2. And a new CY code will be added. That is known as L2C signal, which is there. And later, L5 signal is another one, safety of life signal, which has been added. And later, one more L1C modified CY code is also been added on the L1C signal. So completely on modernization program, you have L1C, L2C, M codes, L5, L3, L4. All will be available this one, and L1 also lies in the ARNS band, and L5 also will be there. So a lot of civil aviation applications will be used, and you have more precise, especially in search and rescue operations. Also, it will be very nice. Good applications will be there. So with this, the existing L2C signal, this signal actually, it is an addition of a new civilian signal, which will be, transmitted on other than this L1C. And now the L2C will act as a redundant signal. In fact, L2C is known as a GPS3 or modernized redundant signal. In fact, if you don't have access to L1C by code, then you will definitely have an access to L2C, because earlier it was not possible in GPS2. And this will be able to provide improved accuracy of navigation and all that. And you will not be able to have much interference also, because now we are having two different signals which are there. So L2C has got two distinct PRN sequence. One is for civilian moderate code length, other for civilian long length code length, and they're all used for the positioning applications. And L2C signal transmission power is around 2.3 dB weaker by code, and it will be able to help in greater carrier tracking. So this signal, once it is implemented, you'll have more immune to RF interference, and also multipath effect also will be, it will be reduced. Next one you have is the that is for M codes. M codes are the modern, that is the military codes, and these are having a lot of anti-jamming properties are there, secure access for a military signal, so signal cannot be jammed very easily, unlike that of the P codes. And these M codes are transmitted in the same 11 L2 frequencies, which are already used by previous military code, that is precision code, P code. And unlike P code, the M code is a very special characteristics. That M code is designed to be autonomous, meaning that users can calculate their positions only the M code. And P code receivers, actually earlier they were used to lock on C by code, then they had to transfer to the P code and all that. They have to be taken care of. So that's the issue which is there, and they need to be taken up. And other M code characteristics which are there, satellites would transmit two distinct signals from two antennas, and modulation is binary offset carrier. And there are different kinds of flexible data payloads which is already available. And it has already included FEC and other error detections. Properties are there. Spot beam 20 dB more powerful than whole earth. All these things are available. The new signal we have, that is L5 signal, which is there. It is known as a safety of life signal. And basically, the radio spectrum of L2 signal is not fully protected through the ITU, International Telecom Union, and it does not lie in the ARNS band also. So therefore, there is a need for new signal. So, and this additional L2C signal cannot be relied upon safety of life application like civil aviation emergency service applications. So therefore, third civilian signal is required. That is 1.1 gigahertz, and this will be very helpful. So this will have an improved signal structure for enhanced performance and high transmission power and wider bandwidth and longer spreading codes. And anyway, it is there in the aeronautical radio navigation service band. It is available everywhere. So that's another advantage. And another new signal which has been added is L1C signal. Apart from L1C by code L2C, this another signal which will help in maximizing interoperability. Like as I said, you 4 satellite signals. It can be 4 GPS signals, but this signal will help in, like, one satellite signal can be GPS3, one can be GLONASS, one can be Galileo, one can be ARNSS, and it will be able to provide, and you can have a use in the multi-constellation receiver. So this is all very, very important in this particular one. And GPS3 will be able to, once it has been implemented, it will be able to have an all better applications, and it will be able to take up in a much better way in the future applications, especially in the autonomous vehicles driving and all that. So these are some of the comparative analysis of L2C, M codes, L5, and L1C signals which are there. Later, once we want all these things to be implemented, we definitely need a new control segment. Existing control segment cannot be used for this particular system. So GPS OCX control segment program, it's a very critical part of GPS modernization, and it provides some significant information assurance improvements over the current system. And this GPS 3 will have a flexible architecture. That's another, because earlier was not that way, GPS 2. And that will be able to rapidly adapt to the changes needs of today's and future GPS users, where it will allow immediate access to GPS data and other information through secure, accurate, reliable information. And definitely this control segment will be able to empower the war fighters with more actionable and predictive information to enhance situational awareness. A lot of AI techniques and other techniques will also be used in this. And it will provide significant assurance and a lot of preventing cyber attacks. This is another one which is there in this, and they will be all will be used during the situational awareness, and lot of higher volume near real-time data command and all that can be sent using this particular program. These are all the milestones which are achieved. Select availability means actually earlier GPS was having that at a particular region they can improve more error, they can enforce more error during any kind of war and all that. And there was some earlier one aircraft accident which has happened. It was shot by the other country when it has entered into their airspace. It all happened because of the selective availability, and therefore it was set 0 in May 2000. And later, it is there like block 3 we want, and this is a new modernization program which will take up in all the 3 segments, and they'll be able to transmit the signals. Now, once you have a GPS 3, what will happen is you will have an accuracy less than the width of a small finger, and definitely you're going to have a self-guided cars. You'll have a better application for constructions. Variable rate practices will be there, and automatic construction. So many things will happen in this particular segment with the new signals, new control segments, and all the things will be there in this particular system. So this is all about that is the GPS 3 modernization program. And apart from that, in fact, we have our own system is also available. That is Indian GPS system, which is known as IRNSS. In fact, initially it was started with IRNSS. Later, the Honorable Prime Minister of India is renamed that as NAVIC. So across the world, people will call it as a navigation with Indian constellation, and it is very well known as India's own GPS. Unlike a GPS, which is a global system, but IRNS is a regional system which will cover only Indian region, and it around 1,500 kilometers around the Indian region. In fact, it all happened during the Kargil war when Pakistani troops took the position in the mountains. Indian military was not able to get access to the GPS of the data, and a lot of things have happened. And therefore, the India realized for importance of indigenous navigation, and therefore the idea of IRNS began to take shape up. So with the help of IRNS, India became a very self-reliant to keep a close watch on it, and it was able to take up. This is implemented by ISRO, and it can provide a position accuracy of 20 meters over Indian region and 10 meters on the land mass, and 1,500 kilometers also will be covered by this particular system. And this service is available for 24/7 in all weather conditions. And in fact, it is also going to provide most accurate services for authorized users, that is the Indian military and all that. Like the architecture of the GPS, IRNSS has also got the space segment, control segment, user segment, and the operation is similar to that of this. Unlike GPS, where the satellites have been placed at a height of 20,200 kilometers, our satellites are placed at a geostationary and geosynchronous orbits. A few are placed in geosynchronous and few are placed in geostationary orbit, so that all the satellite signals are visible to the users across India and Indian subcontinent for 24/7. Whereas GPS satellites are visible only for few hours only. So that's the idea. So our satellites are placed in in the geostationary, geosynchronous. This is what geosynchronous and geostationary orbit, which is there. 3 are geostationary and 4 on geosynchronous at a different angle, which is there. And totally 7 satellites are being launched. That is IRNS 1A, 1B, 1C, 1D, 1E, and 1F, and 1G, and all that. And recently NVS-01 is also been successfully launched. It is there. And this year and next year, many more satellites will be put into this space. So India want to make around 11 satellites to be put into space apart from 7. So and later it will extend for a global system. These are the control segment which is there. And it will be used for all these applications, whatever we discussed for the monitor station, master control stations and all that, they all will be available for this particular system also. And Indian signals, Indian IRNS signals will be transmitted on both L5 and S-band. Unlike GPS has got L1, L2 and all that. S-band is for 2 to 4 gigahertz and L-band is for 1 to 2 gigahertz. And we can have both single frequency and dual frequency receivers. And like PPS for US-based GPS, here also we have SPS and restricted signals. And SPS signals are available for civilian users and restricted signals is for authorized users of US military, Indian military applications only. So like that, we have access to these particular signals. And the weight of the satellite is around 1380 signals and the design lifetime is 7 years. That is there. And this is the IRNSS 1A satellite, which is there. And it will apply to all the applications, civil aviation and all other applications which are there for applications across it. And these are the receivers which I want to show you. These are Navik and Gagan receivers. They are already, this is the initial receiver which are been kept here, and there are multi-mode Navik chips which are there. Chips which are there like a, multi-channel positioning chips are also there. FPGA chips are also there. And ISRO has developed many other SPS ASIC chipsets which are already being developed by different organizations, and also some are developed indigenously also. These kind of setups and new initiatives have been there. And later, Navi plus GP receivers are also been developed for both, L5 and S-band receivers. Combination, you can use both the signals, and you can do the comparative analysis of both the options. And these are all the other receiver chipsets which are already available, which are there. And navigation message services, and these are emergency rescue operations. The messaging services will be sent by these satellites, and they'll be giving you all the information, and the maps will be supported. Special alerts to the fishermen crossing the international boundaries will also be given. Vehicle tracking, this is an indigenously developed by vehicle tracking system, NAVIC base. It's a SAC system which is there, and these can be used for these applications. And these are the timing receivers which are there. So this is the timing receiver which is there, and it will provide you the most accurate time here. And NAVIC chipsets are also been incorporated in the some of the mobile phones, which will give you more precise applications. And many satellites are also along with the other satellite signals. And in fact, Usmania University, we had an MOU with Space Application Center, which I want to throw light on this. And based on that, we developed an advanced research laboratory, and CAS Kiran Kumar sir inaugurated laboratory. And this is the initial receiver where they gave us IRNS, GPS and SBAS receiver, where we were able to do the comparative analysis of all these signals, GPS and all that. And we received all the satellite signals, did a lot of work on this, many people. And apart from that, we had an vehicle and put a GPS, this IGS receiver. We did the comparative analysis of GPS and IRNSS. We traveled throughout the campus, and we got a lot of signal information, signal strength and all this. And at the time, IRS was doing much better, providing you better positioning applications. And we worked on different modes also, L1 signal, L5 and all that. And many of my scholars along with BA and tech students, they have successfully carried out this work and achieved the PhD degrees also. The other concern which are there is spoofing and jamming, which is very, very important factor, which need to be taken care, and that's a very important thing. So existing GPS will have an errors and cannot be used for some of the important applications, and they will not be able to support Cat1 and all that. So therefore, what we require is, this is the precision approaches requirement of category 1, where aircraft decision height is around 200 feet. And that means aircraft can land and take off at a height of this 200 feet. In category 2, decision height is 100 feet and category 3, decision height is 50 feet. That means once an aircraft lands, it will have the capability to again to take off this particular one. So none of the GPS will have it cannot meet 1, 2, 3 requirement. So therefore there is an augmentation system is required. So that augmentation will be helpful in improving the position accuracy of the GPS. Now, like that, many other countries, they have developed their own system, that is United States. So we have WAS, we have Japanese system, and the Indian system is known as Gagan. This is the principle of WAS, which is there. If you look at here, GPS signals are being transmitted. It's an US based region. Wide area US SBAS system is known as wide area augmentation system. It's a United States. Satellite signals are being transmitted, and here we have a red dots. These are known as wide area reference station. They are kept across this particular place, and they'll be able to receive signals continuously from GPS satellites. And from there, they are being sent to the wide area master station, where wide area master station will be able to receive the signals. And there, what will happen? They will calculate the corrections, and those corrections are being sent to the ground uplink stations. And from ground uplink station, the information is sent to the geo satellites. Now, when aircraft is moving over US, what will happen is this aircraft will receive the GPS signals and the corrections from the geo satellites, and it will improve the position applications. So this is not possible with only the GPS, standalone GPS, but it's possible with geo satellites. So with this, therefore, this system is known as satellite-based augmentation system, because corrections are being transmitted from the satellite, and they'll be it will have a very improvement position, and it will be able to meet Cat1 precision approaches. Like India has also started its own system, that is Gagan. It is already in operation, and Indian government want all the aircraft should be having equipped with Gagan system. And I think recently Indigo, they have started with this Gagan system, and it will help in very precise landing and takeoff, and also helps in air traffic controller. And these are the locations which are being kept across the Indian government. And the GPS will not provide, will not meet category 2 and 3 requirements, as I showed you. So that is wide area augmentation will not meet 1 and 2, but this last we require another new system which is there. So that is known as category 3 precision approaches. So for that we require new system which is known as local area augmentation system. Now this is also known as ground-based augmentation system, and it has got ground equipment, ground receivers are there, LGF, VHF data broadcast, and complement by LAS avionics. So if you imagine this as an airport, and in the particular airport, well surveyed location, these GPS different receivers will be kept here. GPS satellites will transmit the information continuously to all these particular receivers, and it will receive the information. Now this information will be sent to the LGF. So last ground facility will be there, and it will calculate all the corrections valid for only this particular airport. And then it will calculate all the errors and all that, and it will format the last correction message, and it will send to the VDB, VHF data broadcast. And this VHF data broadcast will be able to receive the signals, correction signal. And when aircraft enters, it will transmit the VHF data broadcast corrections, and also it will receive the GPS signals. Now this will provide as part of the equipment is there on the aircraft, and part of the equipment is there on the ground. So once this is implemented, what will happen is, aircraft can be, will have accuracy of less than a meter, less than 1 meter and all that. And it will help the airports to take up with more number of applications. Air traffic control can be taken, plus dependency on the ATC, and more number of aircrafts can fly. And even in India also, we don't have this system, and many other lab systems have been implemented across the world, like Memphis Airport, US, Australia, Japan, and many other locations. And prototype of this model has been taken up at Chennai Airport, and they're planning to take up this particular system. So this is the end phase configuration of this particular system. There are a lot of applications are there in we talk in petroleum industry, power grid, space applications, air traffic controller, or personal navigation, transit operations, shipping operations, emergency rescue operations, GPS, vehicle tracking, and all that. So wherever GPS is being used for transportation, it will be used, but for SBOS can be used for search and rescue operations, and GBOS or LOS can be used for aircraft civilian applications like that. All this will be used for different kinds of applications, and similar applications will be there for GLONASS, Galileo, and other constellations also will be available for this particular system. So thank you for giving me the opportunity. So I have taken up all these particular systems which are available, and in fact, I have one video also to be shared if it works out. Let me see. I will share this particular video about the GPS modernization program which is there. I'll share through the Google Chrome if possible. Hope you are able to see the video. Okay, I'll just minimize all the things. I'll stop it. Then I will share again the video part. I think through Google Chrome it can be shared. Yeah, I'm able to show that. Please just the modernization program for this.
And wanted to add some technology doing something like the answer. We wanted some higher quality signals for info to be able to get a jam capability. We're doing the direction we're going, but everybody out there realize that it's significantly improved our refining capability. And so now we'll have the network becoming more. And so we had to do the next generation. And I really think now we're starting to deploy that thing. So we need to start working on what matters. How do we expand and reach every area, and we need to make sure integrity with system to be able to stay forward.
Yeah, thank you. Over to the organizers. So I have covered everything, most of the things.
Thank you for your valuable.
Thank you, sir. Any doubts from participants? So any doubts from participants can. Okay. Okay, thank you very much, sir, for your insightful and valuable information. We truly appreciate the time and effort you have taken to share your knowledge with us. Thank you, sir.
Yeah. Thank you very much for giving the opportunity. Thank you so much.
So participants, please mark your attendance and feedback in given links. And then